But we didn't know specifically which variables. Surprisingly, it's turned out that over time we've learned that a few of the variables were a lot better than we thought. For example, casualty data, if you just look at deaths, our data set is really very good because, quite frankly, they make the headlines. The deaths do. And when you think about how this data set is drawn up by people, we've got, these people are scouring the internets and the media worldwide in all these different languages, looking for reports of terrorist activity of all sorts, both attacks by them and police going after them, and military raids, very rare, unfortunately, but court cases, arrests. And so we have that kind of information, which is also pretty good. I'm saying all that because, as you're going to see, this is kind of like an acid test. Where really is the data good? Where is it really good in the sense that it's really useful? That's where we're kind of headed here. All right, so we're going to simply multiply the conditional probabilities, the posterior probabilities only. It's really kind of probably a multiple of that, and assign the group to the incident based on the highest probability, in quotes, which does assume, if you're going to do a simple multiplication like that, it sort of makes life a lot easier, but it does assume independence, which may or may not be a big deal. I left out a word. Because at the end of the day, this technique actually works, and it does work fairly well. There's a wonderful paper by Holt, H-O-L-T, I don't know if the E is silent or not, Holty, 93, based on a bunch of data sets. And I don't know if naive Bayes ever won the race, but they're always in contention. It's not a bad data set at all. Okay, so we're going to try that out on our data set. We're going to try out what we're calling multinomial logistic. It's a logistic model where directly modeling a function, not the probability itself, but a function of the probability, the log odds, as a linear function of all those xi or jk's or whatever I call them over there. And so this thing is equal to basically a summation of some betas times those xi, xjk's. We have the advantage here in this thing is that if you suspect there's an interaction going on between a couple of variables, you can actually create an interaction term and stick it in this summation. It can be one of your xj's. So we can actually model the interaction directly. If you know about it, which means, I guess, you use CART and come up with the actual interactions. We didn't actually do that in this case. Yeah, okay, as a statistician, I like this, that your probability estimates are all plausible. At least the probabilities are between 0 and 1, which is my reading of Kolmogorov's axioms. That's a good thing. Another one of these holds good techniques. A lot of these things, of course, depend on your definition of good. We will see what you think. You can judge here in a minute based on this data set. And then we did put the data in CART. And you already know, at least I hope, I'm a great fan of CART. I mean, to me, it's just wondrous. And it's got all these wonderful pluses. By the way, you probably have your own set of why you like CART, why you like trees. And these are just kind of like my bias. I just sat down and wrote down what I liked about recursive partitioning and regression trees, which I think I got from R. I should tell you, I want to thank at this point Mr. Cathy and the New Zealand in general, because I used, on this data set, we used, Josh ran a lot of this as well, we used R, we used Weka, and then, of course, the big kahuna, we ran CART and RF. But we like CART for all of these things, and I'm going to kind of demonstrate some of these pluses. We don't have to worry about levels of measurement. It can handle the continuous variables as well as categorical variables. Don't have to worry about interactions between lots and lots of variables because, quite honestly, this thing originally back in the 60s, it was supposed to find interactions. I mean, that was the whole point of it, was to go out and, so it not only can tolerate interactions, it loves them, it's looking for them. No assumptions, no distribution assumptions whatsoever. And you get nice, pretty results, not just knock off your socks kinds of trees, which everybody just loves. E.T., Edwin Tufte, must be really thrilled with the tree as a way of visualizing any data set. The algorithm basically starts in root mode. You all know that. Recursively splits. I was just trying to use some of the words up above in my own little definition. And the tree is allowed, and this was I don't know, my reading of it, please correct me if I'm wrong, my reading was one of Jerry Friedman and that group's big time deals was to let the tree not stop arbitrarily, but or to grow it arbitrarily, but was to let it just go ahead and bloom and then cut back, which intuitively makes a lot of sense because at least there's the chance that as you prune back, you're getting closer and closer to the reality and you're chopping off the random noise, which at least intuitively would tend to affect the little twigs a lot more than they would the trunk of the tree. There are different ways to prune back, but we like the cost. Maybe I should say something about cost. We just used simple cost. Probably cost of a misidentification was always one. Okay? We're not clever about this, so we just used the simplest of all cost curves. All right, and so we get around this problem of overfitting the data. And then finally, random forest. And again, this is just me talking about what I love about random forest. We're going to accumulate an ensemble of trees, which I welcome the word ensemble to the lexicon of all of us number crunchers. We have all of the advantage of trees, plus this wonderful bagging-inspired added accuracy. We have the robustness, which Leo discussed really nicely in his original article about how the technique, you can't fool it, right? You can throw in all kinds of garbage, and it seems to be relatively insensitive to garbage in your data, particularly, and this is the big deal, particularly to garbage in your dependent variable, which is, that's a big deal. Especially us, if you think about it. There's all kinds of confusion, misdirection going on out there in the world of terrorism, and people take credit. You know, if there's a bombing, I mean, you get a lot of credit taking going on sometimes, or as Josh said, no, just dead silence. So the possibility of us blowing is not. We don't know exactly what it is, but it's not trivial, not small. The possibility that we might not get the right group identified. We can handle multiple dependent variable classes. That's another thing. A couple years ago, we did a lot of this same kind of analysis, and we threw in support vector machines and some, neural net stuff and things that were built on, like logistic regression originally. They were built on but dichotomous dependent variables, and they do wondrous things with dichotomous, but the kind of ad hoc jury-rig kinds of ways of combining that into multiple dependent classes is kind of a turnoff, at least to me. Okay, and then of course the key thing here is that at each node the splitting is done not by the total sample of predictors, that is, it doesn't scour all, and this is where the speed and efficiency comes. Data sets like the ones that Dr. Friedman was constructing with 10,000 variables and, 200 N cases. We don't quite have that problem here. Josh said we got 1,000, or essentially N cases, and we've got 87, which is a little bit high for a purist like myself who would prefer to have more in per predictor, but